sort of explain what Chirp Networks is about and what its relationship is to the earlier body of work that I did with trees and how the two are connected. So the Chirp concept is essentially a three-tiered architecture where at the bottom you have very simple devices that need some form of translation because they're not using the standard IP backbone. They are not Bluetooth or Wi-Fi. And the reason they're not is for a variety of reasons, but primarily my focus was on stealth and innately secure systems that would be not detectable because they had no connection to the IP backbone. And that automatically required things like your TV remote, simple devices that somehow had to be translated into an IP packet. And that packet was where I started looking at how nature handles what I call chirp protocols. And that is a simple example of how birds have different chirp protocols, but they typically are short payloads, which the IP backbone doesn't like. I did earlier work, which is on my website, on VoIP packets and how to build a shuttle service so that they got the sort of control loop that they need, which is periodic and time deterministic. I also call that in my slides the quasi-TDMA. So that work is running, that overlay is running on top of a best efforts IP backbone, which prefers large packets. So it's part of how synchronous local machine control loops can be executed by something I call the dual control loop. And we've had some success with this, which I can get into at some other time. So Chirp devices are already here. Here's a simple example of a three-tiered architecture. Notice that the Pollen, the sensor that is being applied, has a lifetime of 14 days, which would constitute to the allergy season that I refer to, the sort of broadcast storm. In this case, of course, the broadcast storm is being controlled simply because you have a device and a translation, which I refer to as the propagator. These are some ideas where this is going. I sort of go into this. I should actually say that I'm getting this reference of massive IoT from Qualcomm's presentation, which really goes into things like low latency, massive IoT, hops. So fundamentally, it's talking about how this is what 5G can deliver. And then the interesting thing is we have in the enterprise and increasingly in the military and other domains, Wi-Fi, open spectrum delivery mechanisms in place, mostly meshed and using tree-based mesh. And our MeshSuite is capable of helping make that transition so that the Wi-Fi enabled systems can handle 5G traffic and, of course, massive IoT. I think I've said everything I have to say here. So there are concepts around night-type embodiment which are starting to develop. For example, I showed you the slide earlier on, or didn't I? I thought I did. Yeah, I thought I showed you. Yeah, I did. Yes, I tend to ramble. We'll do the best we can. So MeshSuite is essentially a body of software and intellectual property that has been developed over the last 20 years. And essentially, it's trying to build a framework so that you can have things like chirp protocols, and you can have integrate quickly commercial AI tools for network topology, etc., based on what this body of work has been working on. And of course, we have prototype software running in OpenWRT and in Java for the NMS that is running on our Atlassian suite. Happy to give you guys access to that. So the simplest concept, the simplest way to explain this is that the self-tuning topology has been given a decision to make, which is we see that the application traffic is starting to become closer to low latency, which means that the backhaul number of hops, which is a measure of latency, is starting, it needs to be decreased. And the system goes through a series of tuning till it gets to something which, of course, here is the best in terms of latency and the worst in terms of throughput, but everything is connected to the root hub. And so it's effectively gets the best response. A better example of how this works is through the flooding animation video, which I think I had, yeah, I had it backwards. Doesn't really matter. In either case, what you're seeing is that as the health is changing, the adaptive control and the dynamic channel management is running, this whole system is essentially dealing with how to deal with, in this case, just topology. There are other simulations that I can show you in terms of how it deals with synchronous management and control. But you can see that things are changing in terms of, there's another, in terms of the DCA, there's another video on our website, which I won't go into, but it actually goes into all of that in excruciating detail. All right, that deals with that. Let's get back to our main slides. You can link on these and they'll give you more information. This is fundamentally what is the translation mechanism by which chirps or digital ants and their ecosystems that function completely differently than IP packets. This is how they communicate, they get on to the propagator. And the propagator in this case is the mesh node that you saw earlier. There's some patented stuff here that I won't go into, but it explains how the system can work. And it's fairly simple. We allocate through various means a periodic interval by which the shuttle buses will run. And of course, the periodic interval itself is dynamic and it changes depending on what's needed. So during peak time, certain chirp ecosystems will be asked to move their schedules to collaborate with others. And that got into some details here in the collaborative schedule, where I essentially model it as asking for tea or coffee at a specific time, and then what will happen if I can't get there. It goes into excruciating detail again. But the fundamental point is at a very high level, there is the dual control that I talked about earlier, which essentially has to work at multiple levels of the hierarchical control system. So you have these autonomous nodes that are acting as translation devices. So these guys don't actually know that they're talking eventually to an IP backbone. And the reason is that you've got a framework which is radio and protocol agnostic. This is this mesh control layer And I go into that here, but this was essentially the slide that we were talking about. So there are applications running in the mesh nodes that have their own private virtual network. And there's a periodic supervisory control, which is really what we're talking about when we talk about the dual control loop, the big data loop. So I think that was covered in one of my slides. Apologies. All right, I think we're done with this. Yeah. This is a simulation of a framework so that we can do a look ahead. And it essentially describes how we built a simulation environment using virtual machines. So these are two examples of why Sharp was interested. Sharp was essentially interested in getting a market share of the emerging IoT market. We worked together to try to work out how Chirp protocols would be helpful with their future products. This system that they built is modular, and by that, it means that you can add cameras at the end of it. This other piece here comes off, so they, for example, can put a camera or infrared sensor. And the other example, of course, is just usual stuff, but this is where they thought they might use a lower frequency like infrared, simply because of the range, to do various interesting emergency communications.